Alright, in the last installment of the video, we were looking at different example reactions and how we take what we see in reality and how we translate that into a chemical reaction. One thing you probably noticed while I was doing that is I was making sure that I could rearrange the atoms I had so that I had the same number of atoms before and after. This concept is called the law of conservation of mass. Whenever a chemical reaction happens, or any physical process also, matter cannot be created or destroyed by those processes. Okay? In chemistry, we have to show this by writing balanced reactions that illustrate those processes. So we need to make sure that whatever we have at the beginning of our reaction, we have at the end, and vice versa. So this can be a challenging thing for people at first. So we're going to look at how this all works and what are some different tricks and different techniques to help you balance chemical reactions. So if I look at a chemical reaction like this, which shows me copper oxide and reacting with carbon makes copper and carbon dioxide. If we take a look at this, you can notice that, okay, how many atoms of each are here. So first I'm going to start off just with a picture because that's what we've been working with. So it says we're starting with copper oxide, so that's CuO, and then we're reacting that with carbon. So that's what we have initially. I'm just going to draw a line in between these, and then we are going on then to make copper metal, and then CO2. So the question with the law of conservation of mass is, can we rearrange what we have at the top of the line to make what's on the bottom of the line? And so we can. If we take this, we can't make what's on the top look like what's on the bottom. Okay, we can do that. We see that we're short in oxygen. So I can't just pull in another oxygen randomly out of nowhere because that's not part of what I started with. Instead, I recognize that in the beginning, the oxygen comes with the copper. And then in the end, when I rearrange this now to make what I have, these two oxygens can go with the carbon to make the carbon dioxide, and I have two copper atoms left over. So what I'm finding by rearranging with the pictures is that I need to start with two copper oxides, and I end up with two copper atoms, and I have one carbon atom to start with and one carbon dioxide molecule in the end. So I check to make sure this is balanced. I look at how many carbons do I have to start with? Well, I have one carbon. How many carbons do I have in the end? Again, I have one. How many oxygens do I have to start with? Well, here's my oxygen on the left-hand side of the reaction, but there's a 2 in front. So I have 2 oxygens to begin. And then how many oxygens do I have in the end? Well, here are my oxygens in the end. I have CO2, so that's 2 oxygens in the end. How many copper do I have in the beginning? Copper, there's 1 in this compound, but there are 2 of those compounds, so I have 2. And then in the end, I have 2 copper atoms here. Okay? So I see that it balances. 1 carbon and 1 carbon, 2 oxygens and 2 oxygens, 2 coppers and 2 coppers. This works out well to do the pictures, to balance things, to look at rearranging. We don't always want to do that. Okay? Sometimes it makes sense to just try to balance it without the pictures because it's time consuming to draw out all these pictures. Let's look at a really simple reaction, which is the reaction of O3 ozone becoming O2 oxygen. On the left hand side, you can see right now I have 3 oxygen atoms as part of the O3. And on the right hand side, I have 2. Obviously 3 does not equal 2, so mass is not being conserved here. So I try to look at what's a common number that the 3 and 2 both can factor into, and that's 6. So if on this side, if I would take 2 times 3, and let me just change the color of that so we keep track of where these numbers are coming from. If I take 2 times 3 to make 6, and 2 times 3 to make 6 on this side, then they're equal. Now, doing that means that I have to have 2 O3s to make my 6 oxygens, and end with 3 O2s. So you can see these blue numbers are the blue numbers down below. And again, checking that with my picture, if I start with 1, here's an O3. If I start with not one of those, but if I start with 2 of those O3s, I can rearrange those to make 3 O2s. So you can see mass is conserved. Let's look at another one. It's a little bit more difficult. So again, I start with looking at each one. Nitrogen, N. How many do I have on the left? Right now I have 1 nitrogen on the left. How many do I have on the right? I have 1 nitrogen on the right. Look at oxygen. How many oxygens do I have on the left? On the left I have 2. How many oxygens do I have on the right? Well, I have oxygen in 2 different places, and in my count I'm going to reflect that it comes from 2 different places. I have 2 oxygens plus 1 additional oxygen. Hydrogen, how many do I have on the left? I have 3. How many do I have on the right? I have 2. Okay, so now I check. Nitrogen. Nitrogen, I have 1 and 1. That's balanced, that's okay. I look at oxygen. 2 and 2 plus 1 is 3, so 2 and 3 is not equal. And then hydrogen, 3 and 2, again, not equal. So I'd say, well, how can I take care of this? When you're going to take care of this, I'm not going to start with the nitrogen. The nitrogen's already balanced, so I'm like, well, I don't know what to do there. I don't want to start with the oxygen because on the right-hand side, this oxygen's in 2 different places, and that makes it difficult to, when it's in 2 different places to balance out. So what I do is I start with the hydrogen. Just like with my ozone, I recognize, hey, if I take 3 times 2 and 2 times 3, again, let's make that a different color so I can keep track of each one. Then that makes 6. When I put that black 2 there, what does that do? It's taking 2 times the 3 on the left side. That 3 came from ammonia. So that means I need to have 2 ammonias to balance this out. 2 NH3s. I look at that red 3. Where does that come from? That means I have to take 3 times the waters, okay, to make that work out. So that's where that 3 comes from. Now, a lot of times people forget, now that I've put a 2 in front of this NH3, that doesn't just change the number of H's, it also changes the N. Because I put this black 2 here, and that is the same as this black 2 here, I also am multiplying the number of nitrogens I have by 2. Okay, so I have 2 nitrogens now. So when I go back and check my nitrogens, they're no longer balanced. But before I start doing that, because I put a 3 in front of the water, from this 3 here in the hydrogens, that also takes 3 times the 1 oxygen I had. Okay, so when I go look at this now, I'm just like, all right, go back. Hydrogen's taken care of, but let's look at nitrogen. Now nitrogen is not taken care of. I have 2 on the left side, and I only have 1 on the right. So I need to multiply that by 2. Putting a 2 there puts a 2 in front of this NO2. That also puts it in front of the 2 oxygens. Okay? So when I look at what I have now, I've got my nitrogens taken care of, I've got my hydrogens taken care of, I don't have oxygens taken care of. On the one side I have 2, on the other side I have 2 times 2 is 4, plus 1 times 3, which 4 and 3 makes 7. So I have to look at, well, how do I get 7 on the other side? What times 2 is 7? And the answer is nothing times, well, no whole number times 2 is 7. And we try to make our balanced reactions with only whole numbers. So what I recognize when you do something like this is that I'm just going to have to say 7, put a 7 there to make that 14. But now that means I've got 14 on the left side and 7 on the right. So really I'm going to have to end up multiplying all of this by 2. And so when I multiply that by 2, I realize I have to multiply everything by 2. It's a lot of times when you are doing this, you realize, well, I don't, 7 is, or 2 is no good anymore, I need to have 4. Okay? And that, whoops, and this 2 no longer works. Again, I need to have 4. And then this 3 doesn't work, I need to have 6. and I should be able to then check everything with my circles, with my model to make sure this all works out. So I start off with, okay, I need to build an NH3. So NH3. My reaction says I need to have 4 of those. So there's 1, 2, 3, 4. So there's my 4 NH3s. I need to start with 7 O2. So there's an O2. I need 7 of those. So there's 2. There's 4. There's 8 because it was easier. And now I'll just get rid of 1. Okay, so I've got my 7 O2s. So taking my 4 NH3s and my 7 O2s, I should be able to rearrange these to make what it is that I have on the other side. So I take and rearrange them. So NO2, so here I got N and O2, and N and O2, an N and an O2, an N and an O2. So now I have all my hydrogens and some more oxygens. So I make an H2O. I make an H2O. I make an H2O. An H2O. I make an H2O and an H2O. When I count it all up, how many NO2s I have, let's get a different color. I have 1. Different color, come on. 1, 2, 3, 4 different NO2s. And when I count up the waters, I have 1, 2, 3, 4, 5, 6 waters. So it works out, balances out just fine. I think we have time to do one more before I reach my 15-minute maximum. When I'm balancing a reaction that has a polyatomic ion, when I do my counts, if that polyatomic ion is on both sides, so if I take a look at NO3, I have NO3 on the left and I have an NO3 on the right. So if that polyatomic ion doesn't go away during the course of the reaction, I'm going to count it up all together. So you can see I prepared that already with my models off on the right-hand side here. I have NO3 all together as a group because I'm going to treat that as a group of things that isn't going to go away. So I start off doing my count. Copper, 1 on the left, 1 on the right. Silver, 1 on the left, 1 on the right. NO3, that nitrate group. I have 1 nitrate group on the left. I have 2 on the right as part of CuNO3-2, part of that copper 2 nitrate. Okay, so copper's fine. Silver's fine right now. Nitrate, not fine. I recognize I need to have 2 times the number of nitrates I have on the left. That puts a 2 in front of silver nitrate. That puts a 2 in front of this 1. Okay, so now my silvers are no longer balanced. So I need to have twice as much silver in my reaction. Okay, so those two match up. So I go back and check. My copper's balanced. Okay, copper balanced. Silver 2 and 2 balanced. Nitrates 2 and 2 balanced. Confirm that with my models. So if I'm starting with a copper atom and 2 silver nitrate compounds, I can rearrange those to make 1 copper 2 nitrate compound and 2 silver atoms, and it works out just fine. Okay? So now later on we're going to talk about how, here we were just talking about how many of each atoms. I can find out that as long as the ratio is what my reaction says, I work out just fine. So instead of, obviously we're never going to do a chemical reaction in lab where we're going to be using 2 silver atoms and 1 copper nitrate compound, but as long as the ratios are the same. So if I use 2 billion copper atoms, I need to have twice as much in silver nitrate compounds. So I'm going to need to have 4 billion silver nitrates. And even billions, we'll find out, is not a large enough number to deal with this. But we'll get to the actual numbers, quantitation of things later on. Okay? So we're just at the end of our time, so hopefully this helped you out a lot.